Dear students, in the previous episodes, we have studied about the deductive approach, inductive approach, mathematical statements and principle of mathematical induction. We also solved some problems based on some of the series. Today, we will be learning how to solve problems based on divisibility and inequality using principle of mathematical induction. Using mathematical induction, prove that 10 to the power n plus 3 into 4 to the power n plus 2 plus 5 is divisible by 9 for all n belonging to n. For the solution, let P n be the given statement. P n is 10 to the power n plus 3 into 4 to the power n plus 2 plus 5 is divisible by 9 for every n belonging to n. In the first step, P of 1 is 10 to the power 1 plus 3 into 4 to the power 1 plus 2 plus 5. This can be simplified as 10 plus 3 into 64 plus 5. This gives 15 plus 192 obviously is 207, which is divisible by 9. That shows that P 1 is true. Now, in the step 2, let P m be true, that is 10 power m plus 3 into 4 power m plus 2 plus 5 is divisible by 9. This implies 10 to the power m plus 3 into 4 power m plus 2 plus 5 can be written as 9 lambda for some integer lambda. Again, this could be written as 10 to the power m is equal to 9 lambda minus 3 into 4 power m plus 2 minus 5. This equation can be taken as first equation. P m plus 1, we will write 10 to the power m plus 1 plus 3 into 4 power m plus 3 plus 5. This could be split as 10 into 10 to the power m plus 3 into 4 raised to m plus 2 plus 5. Here, taking 10 as common, 10 into 9 lambda minus 3 into 4 power m plus 2 minus 5 plus 12 into 4 raised to m plus 2 plus 5. This we have taken the help of the first equation, and after opening the brackets we get 90 lambda minus 30 into 4 power m plus 2 minus 50 plus 12 into 4 power m plus 2 plus 5. Here on simplification we get 90 lambda minus 18 into 4 power m plus 2 minus 45. Taking 9 common, we could again express this as 9 into 10 lambda minus 2 into 4 raised to m plus 2 minus 5, which is divisible by 9. That implies P of m plus 1 is true. Hence, by principle of mathematical induction, P of n is true for all n belonging to n. Now, let us solve one more question based on divisibility similar to the previous one. By using principle of mathematical induction, prove that 41 raised to n minus 14 raised to n is divisible by 27 for all n belonging to n. Now, let P n be the statement 41 raised to n minus 14 raised to n is divisible by 27. P of 1 means 41 raised to 1 minus 14 raised to 1 is divisible by 27. That is, 27 is divisible by 27, which is quite obvious. Therefore, P of 1 is true. Now, let P m be true, that is 41 raised to m minus 14 raised to m is divisible by 27. That implies 41 raised to m minus 14 raised to m is equal to 27 lambda for some integer lambda. This implies 41 raised to m is equal to 27 lambda plus 14 raised to m. Take this equation as the first equation. For P of m plus 1 to be true, we have to prove 41 power m plus 1 minus 14 power m plus 1 is divisible by 27. This could be simplified as 41 into 41 raised to m minus 14 into 14 raised to m. Taking 41 common, I can get 41 into 27 lambda plus 14 m minus 14 into 14 raised to m. This we have got using the first equation. Now, after opening the brackets, this can be easily simplified as 41 into 27 lambda plus 41 into 14 raised to m minus 14 into 14 raised to m. That can be written as 41 into 27 lambda plus 41 minus 14 into 14 raised to m. That gives 41 into 27 lambda plus 27 into 14 raised to m. On simplification, we get 27 common, 41 lambda plus 14 raised to m, which is divisible by 27. This implies P of m plus 1 is true. Hence, by the principle of mathematical induction, P of n is true for all n belonging to n. I hope you must have understood the two previous questions based on divisibility using principle of mathematical induction. Now, we will take up some examples from inequations. Prove by mathematical induction that n is less than 2 power n for all n belonging to n. For the solution, let P n be the statement given by P of n is such that n is less than 2 raised to n. In first step, we will write P of 1 as 1 is less than 2. Therefore, P of 1 is true. In step 2, let P of m be true. Then m is less than 2 raised to m. To show that P of m plus 1 is true, we will have to prove that m plus 1 is less than 2 raised to m plus 1. Now, as P of m is true, that implies m is less than 2 raised to m. That implies 2 into n is less than 2 into 2 raised to m. Multiplying by 2 on both the sides, we have 2m less than 2 raised to m plus 1. 2m can be written as m plus m less than 2 raised to m plus 1. Obviously, this implies m plus 1 is less than or equal to m plus m less than 2 raised to m plus 1. Since 1 is less than or equal to m, m plus 1 is less than or equal to m plus m. This implies m plus 1 is less than 2 raised to m plus 1. Hence, by the principle of mathematical induction, P of n is true for all n belonging to n. Now, students, we have one more example here. Prove by mathematical induction the inequality 1 plus x raised to n is greater than or equal to 1 plus n x whenever x is positive and n is a positive integer. Solution: let P n be the statement given by P of n 1 plus x raised to n is greater than or equal to 1 plus n x. In first step, P of 1 is 1 plus x raised to 1 is greater than or equal to 1 plus 1 into x. Therefore, P of 1 is true. In step 2, let P m be true. Then 1 plus x raised to m is greater than or equal to 1 plus m x. Take this equation as 1. We shall now prove that P of m plus 1 is true. Whenever P of m is true, 1 plus x raised to m plus 1 is greater than or equal to 1 plus m plus 1 into x. Now, as P of m is true, we have 1 plus x raised to m is greater than or equal to 1 plus m x. This implies 1 plus x into 1 plus x raised to m is greater than or equal to 1 plus x into 1 plus m x. Could you guess how we have written this? We have multiplied both the sides by 1 plus x. This can be written as 1 plus x raised to m plus 1 is greater than or equal to 1 plus m plus 1 into x plus m x square. This further can be written as 1 plus x raised to m plus 1 greater than or equal to 1 plus m plus 1 into x plus m x square, which is again greater than or equal to 1 plus m plus 1 into x. As m belongs to n, x square is greater or equal to 0 for every x belonging to R. Therefore, m x square is greater than 0. This implies 1 plus x raised to m plus 1 is greater than or equal to 1 plus m plus 1 into x. Thus, P of m plus 1 is true. Hence, by the principle of mathematical induction, Pn is true for all n belonging to n. That is, 1 plus x raised to n is greater than or equal to 1 plus nx for all n belonging to n. Now, students, as you have learnt how to use principle of mathematical induction to solve problems on sum of the series and divisibility, I have a small assignment for you. Take down the questions. Question number 1. Prove by mathematical induction that 1 plus 2 plus 3 plus n is equal to n into n plus 1 by 2 for every n belonging to n. Question number 2. Prove that 3 raised to 2n plus 2 minus 8n minus 9 is divisible by 8 for all n belonging to n by principle of mathematical induction. Question number 3. Prove that x power 2n minus y power 2n is divisible by x plus y for every n belonging to n using mathematical induction. So, students, we have learnt how to use principle of mathematical induction to solve problems on divisibility and inequality. In the next session, we shall take up some more interesting examples. See you in the next session. Goodbye.